Imagine waking up on a world that orbits a black hole. Your sky is not just stars and a distant sun, but a huge dark circle with a bright warped halo curving the light around it. On the horizon, a thin crescent of a star or a distant sun casts light across your ocean. Clouds move slowly overhead, waves roll in. On the surface, it could feel almost like an ordinary day. But the clock on your wrist is not telling an ordinary story. Every hour you spend on this planet might correspond to years for someone far away. This is the kind of world popularized in science fiction, a planet in a tight orbit around a massive black hole where time dilation is extreme. In a movie, you can watch whole lifetimes slip by in the universe above while you experience only a few days. But how close does a planet have to be to a black hole to make time stretch like that? What would its orbit actually look like in general relativity? How strong would the tides be in your oceans, in your crust, and in your own body? Would there be any way to build a civilization there or even survive for more than a short mission? In this episode, we will explore what physics says about life near a black hole. We will look at the orbits, the gravity, the time dilation, and the radiation, and ask whether a planet like this could really exist and whether anyone could live there. To understand worlds like this, we have to think with relativity's version of an orbit. Around a black hole, space-time itself is curved. Planets and spacecraft follow paths called geodesics, the straightest possible lines in that curved geometry. Far away, these paths look much like ordinary orbits around a star. Closer in, the story changes. There is a special radius called the innermost stable circular orbit, or ISCO. Outside the ISCO, you can maintain a circular path without firing engines as long as you start with the right speed. Inside it, no orbit is safe. If you try to circle any closer, tiny disturbances will grow. You will spiral inward and fall into the black hole. The exact location of the ISCO depends on the mass and the spin of the black hole. For a non-spinning Schwarzschild black hole, the ISCO sits at 3 times the radius of the horizon. For a rapidly spinning Kerr black hole, the innermost safe orbit can be much closer in on the side that rotates with the spin. The closer you orbit to the horizon, the stronger 2 effects become: your orbital speed relative to a distant observer and the depth of the gravitational well you sit in. Both contribute to time dilation. Your clock ticks more slowly than clocks far away. In extreme cases, 1 hour for you could match many years for someone watching from a distant, low-gravity region. This is the idea behind a fast-forward planet near a black hole. But there is a catch. To get such dramatic time dilation without immediate destruction, you need a black hole that is both very massive and relatively quiet. A stellar mass black hole would rip a nearby planet apart with tides long before you reach that kind of orbit. A supermassive black hole, millions of times the mass of the Sun, has a much larger horizon. Near its ISCO, gravity can be extreme enough to slow your clock dramatically, yet gentle enough over the size of a planet that the world is not instantly shredded. So if a planet like this exists at all, it most likely orbits a supermassive black hole, not a small one.
Time dilation alone does not decide whether a planet is habitable. You also have to survive the environment. Near a black hole, there are 2 especially dangerous ingredients: tidal forces and radiation. Tidal forces come from the fact that gravity is stronger at one point than another. On Earth, they lift the oceans and make tides rise and fall. Near a compact object, they can stretch and squeeze entire worlds. For your black hole planet, the key question is, how quickly does gravity change across its diameter? If the gradient is too steep, the crust creaks and flexes constantly. Oceans are thrown into towering waves. Volcanoes and quakes become common. In the worst case, the planet is pulled apart into streams of rock and vapor. This is why a supermassive black hole is your best bet again. For the same strength of gravity at the surface, the tidal difference between one side of the planet and the other is smaller if the black hole is bigger. Then there is radiation. Many black holes are not quiet. They feed on surrounding gas through an accretion disk. Friction and compression in that disk heat matter to extreme temperatures, producing X-rays, gamma rays, and powerful jets. A planet immersed in that environment would be bathed in high-energy radiation, enough to strip atmospheres, damage DNA, and sterilize surfaces. To have any hope of habitability, your black hole neighbor probably needs to be in a low accretion state, not currently feeding on large amounts of gas. It would have a thin, faint disk or none at all, no bright jets, and a relatively calm radiation environment. Even then, you would want a thick atmosphere, a strong magnetic field, and perhaps a deep ocean to help shield the surface from remaining radiation. A world like this would not be a gentle place, but in the right conditions, it might be a survivable one.
So, could anyone actually live on a planet like this? Near a black hole with time running at a different speed? Physics does not rule it out completely. If you choose a supermassive black hole, keep your orbit just outside the innermost stable radius, and place your planet in a relatively quiet environment with low accretion and manageable tides, you can, in principle, have a world where time runs significantly slower than in distant space, without the planet being torn apart at once. The engineering and biological challenges would still be enormous. You would need robust protection against bursts of radiation. You would have to understand how the changing sky, the warped paths of light, and the tidal flexing affect your climate and your ecosystems. Your contact with the rest of the universe would be distorted by time. Messages sent outward would arrive long after local events had passed. Visitors from far away might watch centuries unfold in their own history, while only a few years passed on your world. To them, your civilization would look slow and compressed in time. To you, their history would race ahead. Living here would mean accepting that your present and the universe's present are no longer the same. Is it likely that nature has built such planets? We do not know. We have only just started to image the environments around supermassive black holes and to discover planets around distant stars. But thinking about them helps us see what relativity really means. It turns time from a single shared flow into something local, shaped by gravity and motion. It shows us that in the right place, a single hour for you could contain a lifetime for someone else, or the other way around. A planet in a close, safe orbit around a quiet, supermassive black hole might never be the most comfortable home, but as an idea, it is a powerful reminder that the universe is stranger and more flexible than our everyday sense of day and night would ever suggest.